Again, though, let's talk advanced chemistry, chemistry 2 with Pastor Dan. We're going to look today at two specific order reaction, first and second order. And we're going to do that how the concentration changes over time. Now, in order to do that, we're going to look at a first order reaction and a second order reaction. Now, these two reactions have specific formulas, specific equations that we use consistently always to determine that relationship of time and concentration. All right, now the first one we've already seen. If you remember going back to Chem 1, we looked at a radioactive decay. And a radioactive decay is an example of a first order reaction. So there's two different ways we can solve it. We can either take natural log of the concentration to start, A sub t, or say at the end, A sub t after a given time, divided by the amount we had originally, and that's going to equal to a minus k, a constant, times time. And we'll use that equation if we're solving for k or t. Now, if we're solving for the amount we have originally, that's going to be A sub t is equal to AO E, natural log base, raised to the minus kt. And that's just a button on the calculator. It's like pi, it's 2.1914, non-repeating, non-terminating number. Now, to find k, we take the value 0.693 over t1/2. And just so you know where this number comes, if you take on your calculator a natural log of 0.5, that's half, you'll get 0.693. T1/2 is the half-life, amount of time it takes for half a reactive substance to react through. Now, let's take a look at the problem. Determine the concentration of iodine-131 that remains after 1.224 hours for a first-order reaction if you initially had 2.250 molar and the half-life of the reaction is 14.56 minutes. All right. So we're going to use, because we're looking for A sub t, the amount that remains, we're going to use that second equation. A sub O, we said that originally we had 2.250 molar. K, we said is 0.693 over t1/2. And from the problem, we see the half-life is 14.56 minutes. So take a calculator, 0.693 divided by 14.56, and we get 0.04760 per minute. And our time here is 1.224 hours, but you can see my half-life and my time are the same units. So we got to convert time into half-life, always do it that way. So put it over 1 hour is 60 minutes, 1.224 times 60, and we get 73.44 minutes. So we're going to just take and plug our values in. AT is equal to AO, e to the minus KT. So we take our 2.250 molar times our E value raised to the, it's an exponent, so E raised to, make sure that's parentheses, 0.0244760 per minute times 73.44 minutes. My minutes will cross out, and I'm just going to get 0.3032617. We're going to multiply that by the 2.250. So that's going to tell you what part is left. And we get an answer of 0.06823 molar. That's our answer. All right, now we're going to do another one this time, but with the other equation. I want you to we're going to pause it here. So pause the video. I didn't do a whole lot of time here. Pause the video. Try working through there. Any questions, let me know. Here we go. It's on your own. So I'm going to ask you to find the H. We're going to find T. Using that other equation, ln of AT over AO is equal to minus KT, we're going to solve for T. And our half-life here is 5,715 years. This is carbon dating, actually, not two carbons going out for a good time on a Friday night, but the way of determining the age of a substance. And it is very accurate up to 10,000 years. All right. So there's all the work there. Probably should have told you to pause that. We're going to take ln of AT over AO is equal to minus KT. AT is 0.6667 molar. AO is 3.0056 grams. K is 0.693 over T1/2, and T1/2 is 5,715 years. So when we find K, we end up with 1.213 times 10 minus 4th per year. We're solving for T, so we're going to put K underneath. So the ln of 0.6667 grams divided by 3.0056 grams will cross out, and then we'll take that value and divide by 1.213 times 10 to the fourth. We have 4 sig figs as the least number, so the answer is 12,410 years. Okay, hopefully not too bad. Okay, all right. Let's go to the next one here. So, the second order reaction. Now, this looks slightly different. 1 over a to the t is equal to kt plus 1 over a to the o. And our k now is a value 1 over t1/2 times a to the o. All right, so let's look at a problem. Determine the half-life of a substance with a second order reaction if after 31.223 minutes, the sample goes from 4.0987 molar to 1.09397 molar. Okay, so we're going to use our equation. What values do we have? We know a to the t is 1.09397 molar. We know a to the o is 4.0987 molar. AT is always going to be smaller than A to O. They're always on a decay process. K is unknown because we're looking for the half-life, so we can solve for K to find the half-life. And T is 31.223. So we're going to solve for K. So that means we're going to take and move A to the O, the opposite side, subtract it, divide by T, put our values in. So it's going to be 1 over 1.09397 molar minus 1 over 4.30986 molar, and take that value and divide by 31.223 minutes. When we do that, put it into the calculator, we're going to get 0.0212472 per molar minute. That's our K value. Remember, we said K is equal to 1 over T1/2 times A sub O. So we're just going to swap partners. The T1/2 is going to come up. The K is going to go down. So we're going to say that T1/2 is 1 over K times. So that's going to be 1 over 0.0212472 per molar minute, the value we just found, times 4.0987 molar. My molars will cross out, and I'm going to get 1 over 0.088007 per minute. To find T1/2, then we're going to take the inverse reciprocal of that, and we get 11.363 minutes. That's our answer. All right. Now I'm going to have you do this one. I am going to give you time to do this one. So I'm going to ask you to find the amount original, the A sub O. If after 15.000 minutes there is presently 0.023645 molar, and the substance and the K constant, I'm just going to give you the K constant, is 4.677 times 10 to the second per molar second. You really can't solve it because A to the O, remember, is needed. That's why I have to give it to you. All right, so pause the video, work through it, see what happens. Any question, ltslpd@gmail.com. Like, subscribe, share. Let me know how it goes. Ready? Here we go. And that's our answer. So we're going to solve for A to the O. We're going to find here that we take 42.292 per molar, subtract it from 42.093 per molar. We end up with 1.99 per molar. Take the reciprocal of that, we get 5.03 molar. Okay, sounds good. Hopefully not too bad. Take care. God bless. And tomorrow we're practicing.